In this lesson, we'll revisit some problems that were covered in my lessons on conservation of mechanical energy. We'll see that the work-kinetic energy theorem could be used just as well. So here we have a 3 kilogram mass, and it slides horizontally off a 1.8 meter high shelf at 6 meters per second. Find the mass's velocity as it hits the ground. The work-kinetic energy theorem requires us to find the net force on this mass as it's flying through the air. Let's draw a free body diagram of this mass as it flies through the air. The only force acting on it is its weight, which is m times g, 3 times 9.81, 29.43. Therefore, we know the net force to be 29.43. The distance through which that force acts is 1.8 meters. In other words, that force acts straight downward, so we need the straight downward distance. It's irrelevant that the pig is actually traveling some distance horizontally as well, because that force is acting straight down, so we need the straight downward distance, which is 1.8. We know the mass of the pig to be 3 kilograms. We know his initial speed to be 6 meters per second, so we should be able to solve this for his final speed. And if you do, it turns out to be 8.4 meters per second, which is what we found back when we did this exact same problem using the law of conservation of mechanical energy. We have a cat sitting on a window ledge. The window ledge is 1.1 meters above the floor on the 13th story of an apartment building. The 13th story is 41 meters above the street level, and the cat is going to hop down from the windowsill and land on the 13th floor. So he's going to fall downward 1.1 meters, and we want to find the speed of the cat as he lands on the floor. And we're told that the cat starts from rest. While the cat is in transition from the window ledge to the floor, that cat will be in free fall. So a free body diagram of such a cat would just have a single force, the weight of the cat, which is his mass, 7.4 kilograms, times g, which is 9.81 meters per second squared. That comes out to be 72.6 newtons. That will be the net force on this cat. The distance through which that force acts is 1.1 meters. We know the mass of the cat. The initial velocity of the cat is 0 meters per second, so that term essentially disappears. And if we solve that for the final speed of the cat, we get 4.6 meters per second, which is, again, exactly the same result that we got using the conservation of mechanical energy. So, if there is no friction and no heat losses, we could use conservation of mechanical energy, or you could use the work-kinetic energy theorem. But if there is noticeable friction or heat loss, you cannot use conservation of mechanical energy. You have to use the work-kinetic energy theorem.